we are going to go over Statistics 101. And you may have already taken a statistics course. You may not, and you might be taking one in September. I find they try to make statistics really hard, and it really isn't that hard. And it does fit into what we went over last time about the research question and PICO. So we're going to discuss it in that setting also. Um, and I'm going to try to demystify statistics for you. So this is what we're going to review. The research question and PCOT, review basics of outcomes and analysis, and how to correct for biases. Oh, I don't have a land acknowledgement, so I'd like to acknowledge the land on which I live and work, which is the traditional territories of the Anishinaabeg, Haudenosaunee, and Wendat and Seneca people. And I live and work in Toronto, which is covered by Treaty 13 with Mississaugas of the Credit First Nation, and I use she, they pronouns. And so we're going to review PCOT again, which is the fundamental basis of a research question. And then we're going to review the basics of outcomes and analyses. And then really, here is the secret about statistics. A lot of statistics methods are all about correcting biases. It's looking at the association of one variable and with another variable. And if we do find an association, can we really say with accuracy that that association is true? And and are we correcting for biases, and how much biases are there? That is the basis of all statistics. And so all the complications and difficulty in statistics really just comes down to how good are we at correcting for biases. So I hope that actually demystifies quite a bit. Again, we use this as the format to develop our research question. P for population, I for intervention or independent variable, C for comparison. And again, the I for independent variable and comparison, if you're using an independent variable, the I and the C are the two sides of the coin, right? So independent variable where somebody, for example, what we're interested in is an outcome in younger people. So the independent variable of interest is younger people, and the comparison would be older people. So, and then O, the outcome, and which is the variable we're interested in. And then T is time. At what time frame are we measuring that outcome? So for me, the two most important parts to really tease out in terms of developing your research projects are what is your outcome of interest and what is your population of interest. A lot of times I find thinking about what your population of interest more a better place to start. It's a bit easier. So, and I want you to use that worksheet, and there's questions about the worksheet, in the worksheet about asking yourself what study population interests you. Very often that study population relates to you. So, for example, for me, I come from a background of immigrant parents. So I'm very interested in newcomers, immigrants, first generation. Um, I identify as a racialized person of color, so that population interests me. I identify as queer, so queer populations and their experience. So you see, actually thinking about the population that interests you often relates uh, to often who you are as a person. So think about that and think about that in your worksheet. What we're going to be concentrating on today and where it comes in terms of statistics is really we're going to concentrate on discussing the outcome. The outcome is summarized as a variable, is a variable, is a variable, okay? And we summarize that variable. And we already discussed that, whether you've started your worksheets. And the idea is that this talk today is going to maybe help you get started on your worksheet if you haven't yet. Does this all make sense so far? Okay, let's talk about outcomes in your research studies. When you write a proposal or a protocol or a paper or conference abstract, we always talk about a primary outcome. Primary outcome means there's one outcome that is most important. And one primary outcome is we identify it because if we're submitting a proposal for a grant, we have to choose a sample size calculation, and we have to choose a sample size, like 300 participants, and we have to do what's called a sample size calculation. And that is based on the primary outcome. So you can't do a sample size calculation on two or three outcomes. You can only do it with one outcome. Do you see that? And when you come up with your research question and your research project, it's often difficult to choose one outcome. Uh, you'll see that because we're conceptually interested in so many different things. Is it health outcome that I'm interested in? Uh, like, is it quality of life that I'm interested in? Or is it health access that I'm interested in? And a lot of times the outcomes are related, but you really have to think about which one are you most interested in, or which one is the most important to the community, or which one is really going to change program and and practice. The ultimate primary outcome is considered to be death or survival. So if someone has died, so that is the ultimate. We want to prevent death. However, that's a very rare outcome, we're hoping, in the work that we do. So often we'll use other clinically or socially relevant outcomes like quality of life, or in the field of HIV, we use viral load suppression, or um, and actually we use viral load suppression or viral load being undetectable or not because there's prior studies that viral load response correlates with death. So that and survival. So then actually what we're using, why the reason we're using viral load is that it's a surrogate for survival. Do you see that? So those are other ways that how we choose our primary outcome. There might be secondary outcomes like CD4 count, and CD4 count response, quality of life. So we're going to use, I think, CD4 count for the examples. So does everybody know what a CD4 count is? Yes, no. So when you do clinic with me, or we'll actually have a talk on the basics of HIV. So HIV is a virus, and in the clinic setting, we're able to measure the viral load in the blood. That's the amount of virus per copies per milliliter. And then we also measure the CD4 count, which is the CD4 count is the measure of the CD4 cell, which is a white blood cell. And it's the specific white blood cell that binds, that the HIV virus binds to and replicates in. And so if someone's not on antiretroviral therapy, the CD4 count falls. Okay, so it is given as a number like 200, 248, 400, 500. Okay, so what difference, as an outcome, which is a variable, how can we summarize that variable, or what type of variable is it? What are the most typical types of variable? what we're talking about is a variable can be summarized as either it's a categorical variable, an ordinal variable, or a continuous variable. Okay, so a continuous variable is something like age, where it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and goes up. Okay, and it can even be someone can be 20.94 years old. Do you see that? It's a continuous variable. Uh, a uh, a categorical variable is one where we take the variable and we divide it into categories. So that would be like, let's say, ethnicity. So we divide ethnicity as, let's say, white, black, indigenous, uh, South Asian, uh, Middle Eastern, Latino, Latinx, um, Asian, East Asian, South Asian. So you see, there's those are categories. Uh, um, the most common categorical variable that we love to work with are dichotomous variables. A dichotomous variable is a type of categorical variable, you see, and another term for it is binary. So it's a it it's there's only two options. So for example, the ultimate outcome variable is death. You can see that that's a dichotomous variable. Alive or dead. Do you see that? Yes or no. So we love to work with dichotomous variables. And actually, you can take a continuous variable. So for example, age. So what we often do is we'll take a continuous variable. So age is from, let's say we have participants that are from 0 to 95 years old but we're interested in youth. Well, we're going to pick an age to divide our cohort by, and very often people less than 30 are considered young, um, young adults, and then over 30 are older. So you see, we've taken a continuous variable and we convert it to a dichotomous variable by picking an age, 30, and anybody under 30 is young, and anybody over 30 is old. But you actually have to assign 30, right? So it's anybody that's 30 or equal to 30 that's older, and anybody younger than 30 is young. So we've now dichotomized the age continuous variable into young or old. Do you see that? Um, and then an ordinal variable is a type of categorical variable that has an order. So we like to use ordinal variables, for example, if you are doing a like a Likert scale, for example. So you're asking somebody to about, let's say, their mood. So if they're depressed or not, and you have different categories. So very depressed, medium depression, uh, not at all, and not no. Do you see, like, it's ordinal. It increases over time. Can anybody think of any other ordinal variables that are good examples? I'm trying to think. The mood is the one that's coming to my mind right now.
Pain,
What's that? Pain?
pain.
Yes, that's a great example. Thank you. So pain, you can say the amount of pain. So high level of pain, moderate level of pain, mild level of pain, no pain. Do you see that? Great example. Thank you. So you see that's a type of categorical variable because there's categories, but the answers are in order. There are other types of variables that we're not going to talk about. We're really going to talk about categorical variables and continuous variables. And we really only talk about those two categories because, as you can see, dichotomous variables and ordinal variables are a type of categorical variable, and then there's continuous variables. So categorical variables are the variable has different categories that it could fall into. And then a continuous variable is it's continuous over numbers. Um, and then, but there are other types of variables. So there can be something called, there could be survival data, so which is a time to an event variable. So a time to an event is where, for example, like survival analysis is used a lot in cancer treatment. So we look at a chemotherapy and we look at the time of survival. So how long did it prolong someone's life? That's a time to event data. Or economic analysis. It could be another way that another outcome type variable. But we're really going to stick with categorical variables and continuous variables. So let me show you how this works, okay? You will be in your research projects, you will have your research project with your population, right? Your study population. And let's say you enroll 10 people into your study that met your inclusion exclusion criteria. And then you're doing the data collection of those people, right? Whether your population are people or whether they're clinics or clinicians. Do you see that? That's your population, and you're going to be doing data collection on them. Each of those, each of those participants, whether it's a person or a clinic, you're going to have a variable that you collected data on. So let's take a person. For each person, let's say you have 10 people that you've enrolled, for each of those 10 people, they're going to have an age, right? So one person has the age of 25, another person has the age of 46, another person has an age of 64, right? And so who can tell me again what type of variable age is? Continuous variable, right? And then that person has that person will have another variable that we collected, let's say ethnicity. So the 25-year-old, let's say, identifies as Black. The 56-year-old identifies as South Asian. The 64-year-old identifies as Latinx. So do you see each one has a different answer, right? And you have those answers for all 10 of your participants. And so ethnicity, what type of variable is ethnicity?
Categorical.
Thank you. And then let's say now we're interested in CD4 count as the outcome of interest, right? So you can see age and ethnicity are independent variables of interest, right? We're going to be manipulating them into, let's say, young and old, or we're going to be looking at different ethnicities and how their CD4 count responses. So CD4 counts are outcome. And each of your 10 participants are going to have a particular CD4 count at a particular time point that we're interested in. So who can tell me what type of variable CD4 count is?
I think technically it's continuous, but you would usually make it categorical by putting under 200, 200, 500, or over 500.
Exactly, right? So usually it's a continuous variable. Exactly. But you can convert it to a categorical variable, exactly as was said. But do you see how that categorical variable that you just said is actually ordinal, right? Because there's an order to it. less than 200, 200 to 500, greater than 500. We would call it a categorical variable, but to be more specific, it's an ordinal categorical variable. Do you see that? And then, so you're going to have data for all 10 of those people, right? And when you go to present at a research conference, you're not going to present the raw data for each person. You have to summarize the data. So why is it important to determine what type of variable the outcomes variables are, but also the independent variables? Okay, all variables. Why is it important? It's important because we, how we summarize or how we describe those variables depends on the type of variable they are. Okay? And we call that you're going to, every professor is different. So you take your statistics course. When I took my statistics course, it was called summary statistics. Very often now it's called descriptive statistics. So of your 10 people that's your study population, you are going to have to summarize or describe the the descriptive statistics of your study population. And so we call that also, we're going to summarize in aggregate that we're going to describe in general the study population. And what statistics methods we use and tools depends on the type of variable. So that's why it's important to understand the different types of variables and what type of variable our outcome is, what type of variable our independent variables of interest are. So for for continuous variables, example CD4 count, very commonly, the basically not commonly, the two ways the two statistics, summary statistics that are used to describe continuous variables are mean and standard deviation. And so in a conference abstract or a paper, you can technically only describe a continuous variable with a mean and a standard deviation if what? The data of your 10 people has to be normally distributed. So you can technically only use mean and standard deviation to describe your continuous variable if 95% of the data falls within plus or minus two standard deviations of the middle, the mean. Okay. And technically, if you have over 200, uh, if you have a sample size or your study population is over 200, this is kind of the rule of thumb. Your data will be normally distributed. But if you have less than 200, it's possible that your continuous variable results will be skewed. So it could be skewed to one side or the other. And if it's not normally distributed or you don't have a large enough sample size, then you'll summarize your continuous variable as a median and interquartile range. Okay? Who can describe in words what the median and interquartile range is? So I think it's kind of neat to think about. So you have your 10 people and you have their ages, and then you actually line up in order the 10 ages that they have. And the median, which is also known as the 50th percentile, is the one that is at number 5, right? Okay. So number 5 or 6 or 5.5, or you have to take the 5 and the number at the 5 and the number of 6 and divide them in 2, right? So that is the 50th percentile, is the number that's in the middle after you've lined them up from lowest to highest. And then the 75th percentile is the one that is at the point of that lineup at 25 percent. So that would be between, you would take the age of the 2 and the 3, add them up and divide them by 2. And then the 75th would be that you would take the age at 7 and 8 add them up and divide them by 2. Do you see that? So with age in our study that we're doing with 10 participants, who would we summarize the age as a continuous variable with mean and standard deviation or median and interquartile range? We would summarize it with median and interquartile range because there's only 10 participants. There isn't over 200. Do you see that? Sometimes not if there's less than, not if there's 10, but let's say you have a study population of 200. Sometimes we'll report both. You'll see that. Okay. And sometimes it's nice to report both because if the median is very close to the mean, then it kind of signifies that there's no skewness in the data, that it's probably um, normally distributed. A couple of other points about reporting continuous variables in conference abstracts, papers, and so forth is if you report the mean of your study population or a mean of any variable, you always have to report a standard deviation. If you report a median, you always have to report the interquartile range. There is actually another summary statistic that can go around median, um, which is the entire range. So you can actually do median and range, which is the lowest number and the highest number. I personally don't like to do that because to me, if you report age with the lowest number and highest number, to me, it could potentially be a form of identifying people because you're giving their actual ages. Do you see that? So I don't like using range for summary statistics. With median for continuous variable, I prefer interquartile range. Um, but if you're ever sending me an abstract and you give a median, you have to give the interquartile range in brackets, and that's done as like a median age for like our example so far was 50, 56 is the median age because we had 25, 56, 64, and the interquartile range will be about 32 and 59, right? And you do it in brackets with a comma in between the numbers. Okay, categorical variables. Categorical variables like gender or ethnicity um, or are reported as frequencies and proportions. We use the word proportion, but another word for proportion is percentage. So remember we had 10 different people in our study. So we would say in our study population of 10 people, the median age was 56 in brackets interquartile range 32 to 59 and they identified N3 and with a percentage 30% as Black, 20% as Indigenous, um, and um, 3 as South Asian or East Asian or Asian, uh, um, and and X number other with percentage. So we report categorical variables with the actual number of the 10 that meet that category and the proportion with a percentage. Okay. And that number is called a frequency. So it's so categorical variables are reported as frequency and proportions, but it's just the number that are in that category and the percentage. Does that make sense? Pretty straightforward so far? Okay. So again, for continuous variables, the mean, again, is the average. You add up all the numbers and then like you add up the 25 plus 56 plus 64 and you divide it by 3. And to get the mean the average, which is synonymous with mean. Median, you order up from smallest to bigger and you pick the middle value. And then the mode for an outcome um, with categories is the category that occurs the most. I never report mode, but you'll probably learn that in a statistics course. And again, the summary statistics for categorical variables is frequency, which will often report as a big N. So the big N is the N of your whole sample size. Do you see that? We had 10. And then little n is the number, the frequency that you have in each category and a proportion. And then this also becomes useful if you're writing a study protocol or proposal. You're going to have your statistical analysis section, and you're literally going to write these words. You're going to say, we will be summarizing our descriptive statistics using standard procedures, describing continuous variables with a means and standard deviation. If the data is normally distributed, and medians and interquartile ranges if they're not, and categorical variables using frequency and proportions. Period. Do you see that? Okay. Any questions about that? Pretty straightforward, trying to demystify statistics. Okay, the next thing that the reason why the type of variable the outcome is important. Now we're going to get into analysis. We're going to look at whether age is associated with CD4 count result. Okay, so if the outcome is dichotomous, we can use something called, we can do 2 by 2 tables. Okay, so let's take age. So we've divided it into young and old, but that's our independent variable. Let's take outcome CD4 count, but let's just dichotomize it. Let's say greater than 200, less than 200. Okay. So then what you'll have is you'll have a 2 by 2 table with young, old, and low or high CD4 count. And the type of analysis you're doing to see if there's an association is a 2 by 2 table. And the statistic that you're reporting that association in can be an absolute risk reduction, a relative risk reduction, number needed to treat, but more specifically, the type of statistical test you use to see if there's an association is called chi-square test or Fisher exact test. I don't want you to completely, uh, you don't have to completely know all of the specifics of this. Okay. But then let's say, and actually this doesn't have to be just if the outcome is dichotomous. Really, it's if the independent variable is dichotomous. So let's take, if you have a continuous variable, right? So let's take age as continuous, and we're going to look at the difference of age between the low CD4 count and the high CD4 count. So let's see, the low CD4 count mean age is 56, and the high CD4 count group, the mean age is 36. So the conclusion might be that it's older people who have lower CD4 counts, right? Those are two means that we're comparing between the two groups, and we're looking at the difference. We would use a t-test. If we are if the continuous variable is not normally distributed, we would be using medians, remember? And so in the low CD4 count group and the high CD4 count group, the one group, the low CD4 count group, the median might be 50, and the for the high CD4 count group, the median might be 30, and we're comparing the two medians. The the statistical analysis test that's used to compare medians is called Wilcoxon rank sum. For time to event, we report we report hazard ratio or Kaplan-Meier curves, and the statistical test is called log rank. I don't want you to really know the specifics of all this, but the thing that's important is the type of variable you have and that you're comparing dictates what analysis test that's used, and also what how we summarize the effect size, like if there is a difference. So if it's a dichotomous variable, we use chi-square or Fisher exact test. If it's continuous, we use t-test or Wilcoxon rank sum. And if it's time to event, we use log rank. We're not going to go through the specifics. What I really want you to get out of this talk is understanding what type of variables, whether they're continuous or categorical, is the most important. And that is what dictates what your summary statistics are going to be, how you're going to report your effect size, and what statistical test you're going to use. So the other examples are if it's ordinal, you use a chi-square trend test or Cruxwell-Wallace if you have to use median. Non-ordinal, you can see there the tests you use. Uh, chi-square test for independence or ANOVA for non-normally distributed. Pre and post test data are often continuous variables. So you have a survey score before they did the training and then one after. Because the sample size, your study population is the same and they're correlated, then you're doing a paired t-test. And then if you're using medians, it's Wilcoxon sign rank test. And if it's continuous variables, um, you can also use uh, a McNamara's test. I saw that there was something in the chat. Are there any questions? Okay, so this is, for example, a two-sample t-test for a continuous variable. This is done the other way around, where you have the young group, group one, and then group two, the older group, and you have a mean CD4 count there, 326 for one, 350 for the other, and then you see how we're reporting the standard deviation. And is there a difference between the two? 326 to 350, and you get a p, and that t-test gives you the p-value of 0.08. And then categorical variables. So here's an example where we percentage that have viral suppression less than 50. Group one, 89% reached, or 400 had viral suppression, and group two, 300 did. So that is the number, and so that's a frequency. And then the 89% and 75% is the proportion. Is there a statistical difference between the two? Because they're categorical variables and we're comparing percentages, we're using chi-square, and a p-value is 0.03. So the difference between chi-square test and Fisher exact test, Fisher exact test is done by hand and is more accurate. And chi-square testing uses the computer to do some estimations. And so if you can, Now it's quite a bit easier to use Fisher exact test. So technically, um, you might want to write Fisher exact test as your comparison of choice for frequency and proportions. But in the old days, Fisher exact test was done by hand, and Fisher exact test would have to be used if you have a small sample size. So if your sample size is less than even 50, you would have to use Fisher exact test for the comparison of proportions. If your sample size is greater than 50, most likely the data is like normally distributed, so you can use the estimate, which is done by computer, which is a chi-square test. But now that we have computers that can do Fisher exact test, technically you can use Fisher exact test for everything. So you can say either actually. Okay, what is a p-value? Is this okay for everybody so far? Everyone gets it so far? Any questions? So now we've gone over summary statistics that you're doing to describe your population based on continuous variables, categorical variables, right? So continuous variables you're describing using means and standard deviations, medians with interquartile ranges. Categorical variables you're describing using frequencies and proportions. And we went over the tests that you're using to make comparisons between groups. So for continuous variables, we use t-test or Wilcoxon rank sum test. And for categorical variables, like we compare the proportions using Fisher exact test or chi-square testing. And what those testings will do for comparison of really two groups, for all of those tests, it's only the comparison between two groups. It will give you a p-value. And the p-value is the probability that the finding observed difference um, it it the p-value is the probability of finding an observed difference if there were no difference between the treatment groups. So we arbitrarily say that a result is statistically significant if the p-value is less than 0.5. And you see, that's arbitrary. So that means that if, like, so here um, in here in this example, the p-value is 0.03%. We can say as analysts that those two values between the groups are 95% for sure that that is a true difference. But there's a 3% chance that that difference is not real. That Does that make sense? So, and globally, it has been chosen that if something is 95% for sure to be real, that is accurate. That is an accuracy that we're willing to accept, and that a 5% chance that there isn't any difference is small enough that we're willing to accept that that difference is true. Okay. And so but there is a 1 in 20 chance that um, of an event not actually of a difference being true. The closer the p-value is to 0, the more statistically significant a result is. Ideally, you're probably thinking now, well, then why don't we set the p-value at 0.01? Wouldn't that make sense? I would prefer to be 99% accurate, but you would to be able to get a p-value of 0.01 so that's 99% accurate, then you would need the you would probably need too big of a sample size. So picking a p-value of 0.05 is sort of a global accepted average acceptance for tolerating it to say something is significant, where there's a potentially a 5% chance that there's no difference between groups. Okay, how are we doing? We're getting close to time. So, sorry about that. I know because I thought we were starting at 1:30. So we can continue or we can stop and do this part later, which is talking about I think that what someone brought up, which is confounders. So a lot of statistics has to do I'll give you a prelude. So a lot of statistics has to do with trying to rule out and remove confounding. So the outcome is our dependent variable. So in this case, it was, for example, CD4 count. The independent variable, so in our case, it was age. The other words for independent variable, it really depends what field you're studying in. You might use the word correlate, you might use the word predictor. If you're studying epidemiology, it's called an exposure. So has anyone heard that? Um, it's so when you if you do a master's in epidemiology, the independent variable is going to be called the exposure. So the idea is, for example, people could be exposed to cigarette smoking, yes or no. So you see it's an exposure to cigarette smoking. And the question is the exposure of cigarette smoking associated with the outcome of lung cancer? So that's why it's called an exposure. So I think I'm going to stick with the word exposure because I'm trained as an epidemiologist. But that's also something that's a little bit confusing because we use the same word. We use different words to describe the same thing. So independent variable, exposure, predictor, correlate, risk factor, those are actually, they're all synonymous. Okay? Dependent variable is synonymous with outcome. And so we'll end on this one. What is a confounder? A confounder is an extraneous variable, so like an outside variable that correlates positively or negatively. You use the word impacts, that's true. But another word we would use is it correlates with both the dependent variable and the independent variable, the exposure and the outcome. And so that the perceived relationship between the independent variable and the dependent variable has been misestimated due to failure to account for the confounding factor in terms of a spurious relationship. And so then you're potentially, so let's say, for example, back in the 1950s, they thought actually that it was yellow fingers. Yellow fingers what was associated with lung cancer. So yellow fingers was the exposure of interest and the outcome was lung cancer. So they think that the exposure is yellow fingers. And when they did their study, do people with yellow fingers have more lung cancer? The answer was yes. People with yellow fingers have more lung cancer. So, oh my goodness, we shouldn't have people with yellow fingers. But what was the confounder? Smoking cigarettes. So smoking cigarettes is correlated with yellow fingers, and smoking cigarettes is correlated with the outcome. So it's important to consider confounding, and that's just sort of like an obvious example. But if you reverse it, if cigarette smoking is the exposure of interest and lung cancer is your outcome, and the association is there, is cigarette smoke, is yellow fingers a confounder? It is potentially a confounder, but what we do, and a lot of what we do in statistics are methods to handle confounding and to get rid of confounding. And those methods include stratification. So we might take people who smoke and stratify them. So in the group of smokers and in the group of non-smokers, stratify people who have yellow fingers, yes or no, in both groups. Or randomized controlled trials. That's why we love randomized controlled trials, because we are randomizing with a flip of a coin, and then all the confounders are randomized equally between the two groups. And then the one we love and we spend so much time doing is something called regression modeling. And if we the next time we'll go over regression modeling, but and we do regression modeling where we have our outcome and then we have our independent variable of interest, our exposure. And then what we can do is we can add other variables that are possibly confounders into the model, and we can adjust for them so that we get a more accurate effect size of what that relationship is, accounting for confounders. And who can tell me what you think dictates what kind of regression model we use? It's been the theme of the whole talk. The type of variable. So if it's a continuous variable, if your outcome's a continuous variable, we use linear regression. If it's a binary outcome, we use logistic regression. And if it's time to event, it's Cox regression. So that's why I spend so much time really thinking about what type of variable your outcome is, and your independent variables are, because that dictates so much in statistics.